to it, and I'll send you the recording.
Yeah.
Okay.
Afterwards.
Thank you.
Okay. Have a good time.
Thank you, Rebecca.
You're welcome.
I have shit. Rebecca. Shit. Someone wrote me that the link is not valid.
What? What's not valid?
Hey, Robert. No, it's working. I'm here, so it's fine. Don't worry.
So you clicked on US 02 Web Zoom.
Yeah, like on the link you sent, it's fine. It's working.
Yes.
And maybe they didn't get that you need to put in a meeting ID. That can happen.
Okay, so
Imitație, roșață și căpături. Cei care vin au bani.
Let's see, is the cluster on?
okay, so we wait for 2 more minutes and then we'll start.
Hi everyone.
Hi. I'm back. So for all the participants, I will ask you please mute your microphone so you can unmute if you have a question. And then I'll ask Claudiu, how do we do? Do we ask questions during the presentation or you want at the end? How do you prefer?
Probably at the end.
You prefer at the end, okay.
It's a lot of stuff doing, and if we sidetrack, maybe it's hard for people to understand. So.
Okay. So then I'll share my screen. We can start with there is a person who has problem joining. I don't understand why. For me it worked, or I guess for the other people it worked. Okay, so I will stop your screen sharing and I'll share mine. Okay, so since this is the first event by an AI Strasbourg, so we are in a collaboration with Deep Learning AI with the team of Andrew and G. I guess the majority of you know him from Coursera and from Stanford. So he has a video, 4 minutes video, where he presents his team. And if you subscribed, if you read all the description of the event, you could subscribe also on their Google form. And you can get I guess a 50% discount for the online courses that they provide. And I will let the video play 4 minutes and then I will come back.
Hello, deep learners. I'm Andrew, founder of deeplearning.ai, and I'm excited to welcome you to our global deep learning community. I know that many of you are here today because you want to break into AI and build your career. I hope that being part of this community will help you to do so. To give you a proper welcome, I'd like to show you around the deeplearning.ai offices and meet some of the teams so we can see where it all happens. Oh, hi. Do you want to tell our friends at Pine AI what you do at deeplearning.ai?
Sure. Hi, everyone. I make articles and other media that help people learn about AI and help them understand the huge impact that AI is having. Today, I'm putting together the next issue of The Batch, our weekly newsletter, and I'm looking for the biggest stories of the week to keep our readers informed.
What's been the most surprising thing you've run into working on The Batch?
How much is going on in this field? There is never a goal. You might think from the outside that machine learning engineers really understand everything about AI, but nobody understands everything about AI because this field is just coming to life right before my eyes as I put this thing together.
All right, I know you're really busy, so I guess you get back to it.
Thanks. See you later.
Oh, sorry.
Let's go meet Kian, who helped me create the deep learning specialization. He's working on an exciting new project. Hey, Kian. So, do you want to tell the people at Pine AI what you're working on?
That's true. A new project that we're there on, focusing on helping people get started in AI and navigating their career by testing their skills, preparing for interviews and certifying them, as well as matching and referring them to good jobs in AI.
That's really cool. And what's the most exciting part of your day?
The AI field is new, organizations and jobs are still misunderstood, so I'm excited to help people understand what different types of jobs exist in the field, what tasks they will work on, and what skills are needed to achieve those tasks.
That's really cool. Well, it's nice chatting you. And now let's go chat with Paul, who is on the product team. Do you want to say hi to our friends at Pine AI and let them know what you're working on?
I would love to. Hi, everyone. I lead the product team deeplearning.ai, where we create AI education content accessible to people all around the world. People like you.
And what are you most excited about right now?
I am so excited to see our community grow and to see how eager people are to learn more about AI.
Thanks, Elsa. So, as you can see, our team is working hard to support you and help you learn. It's never been easier than before to break into AI. So if you want to build a career, you can leverage online resources available, including open source code, data sets, papers, and online courses like the Deep Learning Specialization and Coursera. As part of this journey, I hope you get your hands dirty too. Don't be afraid to dive in to build your try to replicate a research paper and get excited about it. One thing that I've seen a lot of people succeed is in fact, I hope
sorry.
that this
So that's the video. Sorry, can you? I will mute everyone. I don't know who's. Okay, so I will let now Claudiu Vintila, the speaker from today, I'll let him introduce himself. And good luck with your presentation, Claudiu. So I'll make you host. Just a second. Host.
Okay.
So Claudiu, just 1 second. Since you're the host, sorry, but you'll have to mute the people if you see that there is noise because someone is speaking without asking questions. I cannot do it anymore.
Okay. Also, if you have questions during the talk, type them and we'll get to them at the end. Okay. Okay. Hi everyone. My name is Claudiu. I started my career as a backend developer doing PHP and Java Enterprise. Eventually, I took some time off and started learning machine learning. And I joined a company a few years ago to start my machine learning career. And there was a need in the company to go to production. So I started doing basically infrastructure and code architecture, so we can deliver and scale the application as we do it. So basically, that's my background, and today I'm going to show you how you can take a model and do a little bit of refactoring, a little bit of architecture, code architecture to split it in microservices, and then how you can deploy it to cloud and eventually scale it as the load increases. Okay. Now let's see. Not sure how to do this. Okay. So I guess you can see my screen now. So the way I decided to do this presentation is basically create a repository in which I take code. I took actually code and did the steps. Each commit is basically a step, and we'll go basically through all the commits, and I'll try to explain each step, and we can see the changes in the code and how it evolves. Okay, so let's see. Let's go to the first one. So this is how the okay. Let's hide the rest.
Claudio, we can only see your video, not your screen.
Video, okay. Let's see video. No. Okay, share screen. Can you see it now?
No.
Share screen. Okay. Okay. Yeah.
Yeah, works.
Okay. So basically, the first thing you should think about when scaling is basically how you're going to scale development also. So you'll be working in a team. Usually people when start developing machine learning projects, they do in Python notebooks, which are fun to prototype, but are really hard when you're working in a team and you're going to share code and deployment strategies and so on. So I will also show you a little bit of productivity tips. I will be using an IDE that supports run configurations for Python, also debugging and so on. So, okay. What I did in my first commit, I set up my IDE, and also I have also a step file where you can install the dependency I used and configure things and try to replicate what I've done. So basically, if you're gonna install this IDE, you need to set up the Python interpreter. This is a free license, the community edition. So everyone can basically try it. We'll be using Python 3.7. After install the IDE, you should set up the interpreter and virtual environment. Virtual environment for Python will let us basically install dependencies that we need only for this project, and they will be installed here in this folder. I already done that, so we don't waste time with that. Here in the requirements text file, you can see what we used. So if you're going to try to replicate this, make sure you use the exact same versions, as some of them will probably break if you use newer ones. There's also one package that I did the fork on, and that combines Flask and RabbitMQ, and that's not, I didn't do a package for pip, so this is going to be installed from this location in the repository. So yeah, okay. Let's see. So basically, we're gonna start with this, move to the next commit. So what I took here was this file here. So basically, this is the example that you will find on scikit-learn.org. It's the example for detecting digits using NIST. So I took the exact code that you would find there. Let's open this. I also found out how you can dump the model and load it, and also code that helps us to do a prediction from an image that we're going to supply. And I also did for each step run configuration, so we can run the code and see basically how it works. This is going to be just a simple run, no extra parameters. So if we're gonna run this now, we should be able to see the learning. Okay. Okay. So basically, it uses I don't remember which classifier. Let me see. Support vector classifier. Okay. So this is a support vector classifier. It splits the data, it trains on it, it tests, it prints out some statistics, and it also builds the confusion matrix, which we can better see here. This is the results that the training does, and this is our examples from the training set and test set. Okay, so I also added here, let me uncomment this because we won't be using this further on. Okay, I also did a prediction on images that I have stored here. So basically, I This is the image that I downloaded from the internet, and this is what I tested here in the code. So this is 5, and it detected here the class 5. This is the code for the prediction. Okay, so basically this would be a usual workflow for some code that you played with. So let's see. The next thing what we want to do now is split it into microservices. Now, okay. Why do we want to do this? Well, let's imagine that you want to take this to production. Now, if you're going to have only one model, that's pretty simple. So you don't need to scale that much. But let's say that you want to have, I don't know, prediction from models are built on different training sets. So for example, you would have, I don't know, 10 customers or clients that you want to sell your, I don't know, service as a SaaS, and they each have their own data set. You cannot mix them. Each one will have its own training, prediction on its model, and what's also a very common case is that new data is added to the training set. So that means that basically you need to generate the models on request and start using the new models and so on. So basically this is the scenario that I'm going to show you today. How are we going to do that? In order to do that, we need to split it into microservices. One is for training and one is for prediction. And this is what we're going to see now. So basically now we have created two files, the predict and train, and these are the run configurations for those files. So let's open those up. Basically, okay, let's do the train first. That would be the obvious one. So I took all the train code from the digits file, cleaned it up a little bit only with what we need. At the end, I did the dump of the model to a provided model path, which will be a parameter for our function, and that's about it. So this only does the training. Sorry. Okay. So we have now also run configurations for this. Let's run it. Train. Okay. If we run the train, what we're going to see is just the stats for our training, and we save the model to this location. Now, we're not going to handle the storage of the data sets because that's usually a trivial job. You have a database, you save it there however you want, and you just pull it, pull the right data set at the training time. So we're not going to do that. It's just going to complicate our process. Okay, so we have the training. Let's see the predict. The predict is basically the same thing, which you take the image, you grayscale it, resize it to 8x8 pixels. You need to do an invert because that's how the model has training on. So the prediction needs to be in the same way. So you need to do an invert. You transform into NumPy array. There's also normalization on the data, which I also did here. And there's a reshape here. And then we just run the predict on the model, which the model is the one that we loaded. Also, the path is provided here as a location where this will be taken from. So, okay. We also did here the same image, a test on that. So let's see if we run the predict. We'll see. Okay, we got the same answer. Class 5. Okay. Okay, let's see what's next. So basically, because we're going to build two microservices, let me open the presentation. There is a little bit of, yeah, I think that's right. Should do. So basically, we're gonna have two services. We're gonna have an API that wraps our code, web service API, and workers. The API will expose two endpoints. One will be to trigger the training, and one will be to predict. And the flow, the workflow will be like this. The training will be triggered to start. We're going to use a work queue for the management of the jobs, and the reason we want to do this is because there's a lot of things that can happen in your code if you just call directly from the API to the worker. There's a lot of bugs that can be either in the API or in the worker and can crash it, and then you have to decide what to do when that happens. And you basically need something stable that handles the jobs. Also, something that's scalable. If you're going to do it in your code and you're going to handle the parallelization using threads and processes, that's going to be usually very complex for somebody, and you need experience in that. So we prefer to use something that handles all those problems. Okay, so basically we're going to use RabbitMQ, which is a queue management tool, and we're going to create queues, and the API we call the worker queue, and it's going to put a message in the worker queue, and then the Rabbit MQ will handle the delivery of the messages to the workers. So basically, what we want is the message to be consumed by the workers one at a time. So the first message is going to be handled by the first worker, the second by the second worker, which should be to here, and the third message by the third, and the fourth message is going to be handled again by the first. So this is going to be a round robin strategy. After the model is trained, we need to use it. In order to use it, we want to notify all the API services that a new model was created, and they need to use it. So again, we're going to use a queue, but this time we're going to use a fan-out strategy. So this means that when a model is built and the queue is notified, all of the API services will be notified so they can start using the new model. Okay. Now, in order to do this, we need to connect and communicate with RabbitMQ. For this, I have prepared a consume module and a publish module. Okay, let's move on and look at those. Okay, should No. Okay. Now this is the exact example that you're going to find here at the Kika module. And basically what this does is handles in a thread safe manner the connection to the rabbit enqueue, and it starts consuming a queue. So basically you will tell it what exchange to use, the type, and the queue that it is connected to. And after, there will be some callbacks here, and after it is, where is it? Acknowledge message. Yeah. So this is the callback that basically does our work. They put a sleep here for 10 seconds. And after it finishes, you need to notify the queue that you successfully did the job. So this is what the acknowledge message does. So this basically makes the job management very efficient for us, because somebody will manage, will make sure that our jobs will be completed, and if something happens, the job will remain in the queue, and you can go and debug and figure things out. Okay, and this is the publish example that you will find also on the site of the Pika package, and basically it's more or less the same. You want to create a connection to the RabbitMQ, specify the exchange, the queue, the type, and so on. And you just do a publish to the queue. That's basically what you need to do when you publish messages. So we took these examples, and in the next commit, we're gonna see how much we modified this, adapt them to our needs. So let's see. We will have a consume, and basically what we did is just put this in another method, parameterize it. We're gonna use a callback, exchange, and queue parameter that we're just gonna call this. And what we've done is also added a final callback that is gonna be used for the final task. Okay. And a publish. It's more or less the same. We put it in a method. We will also be using some environment parameters for the user, password, and host. So we're gonna see this later, how it's gonna help us. Okay, now let's see this in action. So basically, I will should have a working queue, RabbitMQ server, and okay, and basically can run these components. Let's see. So first we want to do the consume, start the consumer, and seems that it's waiting for, it's connected and it's consuming the queue. We can also look exactly what queue it does. So basically I've done in every I don't know, files, I've done a main, so we can call this easy. It's gonna call back on this method. It's gonna consume the worker queue, which is attached to the worker exchange. And now we're gonna publish a message to the queue. Okay. And we should be, okay, so it's sending the message, send the message train nest, and the consumer intercepted the message and it printed it out. So basically, this is how the communication between our microservices is going to happen. Okay, now let's move on. Now we're going to build the worker. The worker should be pretty straightforward. Let's stop the consumer. Okay. Let's open up the worker. So basically, the worker is going to start consuming. I'm going to be using the consume module. It's going to use the callback that we are defining here. And it's going to be consuming the worker queue that we define in an environment parameter, which is attached to the worker exchange. When we receive a message, we check if it's train nest, and if it's that, we're gonna train the model, trigger the training, and tell it to save it at this location. And after that, we publish another message with which is going to be cache nest. So we trigger the caching of the models in the API components. And here we also define the exchange to which we publish, which is a fan out, and we also configure it as durable and define also the delivery mode. Okay. So basically, this is all what a worker needs to do. Just wait for messages, train when it's triggered, and notify the other components to cache the new model, so they will use it. Okay, now let's see how the API would look. Now the API is going to be a little bit more complex. Basically, it's going to expose the two endpoints that I was talking about, and also listen on the API worker queue for when to reload the cache. Okay. So basically, what we used here is Flask, which is a very common web service framework or micro framework in Python, and there's also an integration of RabbitMQ with it. So basically, that's what we're going to do, because in this case, we'll have basically two threads that will be running in our component. One is the Flask, which waits for HTTP requests, and and the other one is going to be the RabbitMQ, which waits for queue messages. And okay, and let's have a look. First at the API. Okay, we're going to look at how defining what the web service for the train would look like. So we define the root train, which is a post method. We define what arguments is gonna receive. It will be JSON. It will be receiving a string type with the key action. If that action is train, will be equal to the value of that. If that will be train, you will have to publish this message, a message to the worker exchange with the message train nest, so that one of the workers will eventually pick that up and train a model. So that's basically it for the training. The worker will then process that and will publish a message to the API exchange. So we're gonna have to do a callback here, configure a callback here for exchange type fanout with the same name, API exchange. And basically, when this will be called, we do the reload of the cache and also acknowledge the message in the queue, like we did in the worker. And this is basically the code reload for the cache. So the way I did it is we are using a cache. Each API will have a local cache in memory so that when you do the predict, you don't load the model from the file system. You hold it in memory and just use it to have a better, faster response when you do the predict. So basically, this is what we're going to use. We are going to use the cache for, and we do a load of the model and set in the cache with the same the key of the location on the disk, so it's easier to manage. And we print a message that we did the cache flow. I also did an endpoint for the predict. Basically, it handles an image upload. It checks if the image was uploaded correctly using the HTTP protocol, and at the end, where is it? I'm missing something. Okay, I forgot to call the. Forgot, just hard coded it. Yeah, here should. Yeah, here should be a line of code that just calls the. Let's see. Predict. Yeah, I forgot to do that. Hope that this doesn't crash. File save.
Claudiu.
Yeah.
Do you want to make it work to run it right now? You can share it maybe after and just explain principle on blocks, code, what they are doing to be easier to follow, because I'm a little bit lost.
Yeah. Okay. We're gonna leave it like this then. It's probably better. Okay. So basically here would be the predict, which will return the prediction on that image. Okay. So now we can also run the API. Let's see. Okay, and we start with the worker. Okay, so the worker is now consuming. The API is running, and we can now basically do a test. So we'll be doing on localhost train. We're gonna post this JSON to the endpoint. And let's see. And this is what it returned. So now if we look here, we'll see that it got the post. It sent the message to the queue, to RabbitMQ. And if we look at the worker, it intercepted the message, it did the training, it saved the model here, this location, and it sent the message cache missed to the other queue, which was intercepted by our API and basically reloaded the cache. So basically this is the, I don't know, architecture that you would want to implement in order to eventually be able to scale this. So now if we're at this state, we can start to move on to see how much we can deploy it and basically scale as much work as we want, and also API components to handle a lot of load and training of a lot of models in parallel, and also serving them after that. Okay. Now, the next step we're gonna look at is containerization. So all this code needs to stay in a container, in a Docker container. Okay, let's have a look at a little bit at the Docker architecture. So basically, this is a short comparison between traditional hypervisor or traditional virtual machine and a Docker solution. So you will have the host system on which you install Docker, and Docker basically uses part of the host system kernel, and on top of that, you basically virtualize containers in which you will only be installing your libraries and then your application code. This is more fast compared to virtual machines because Docker basically reuses the kernel. In this case, the Linux kernel, and compared to virtual machines where you basically would install the operating system in every virtual machine, and that solves pretty much your solution. So basically, we're going to use Docker. We're going to create an image with the all the OS and libraries, and we're going to install our apps inside those containers. Okay, let's try to have a look a little bit at our Docker files. So the way I did it is I created a Docker base image, which will be then used as the base for our API and worker. So basically, how a Docker file works is in the same way like you would work with objects and classes in object-oriented code. Images are basically the classes that you define, and the containers are basically the objects. So a class would extend a different class. So this is basically what the Docker file on image does. It takes a pre-existing image, and then you would run your custom setup here. So basically, what we do is copy the requirements that we listed locally in our virtual environment, Python virtual environment, and we're gonna copy that, use pip to install all those requirements, and also I also installed the Flask RabbitMQ that I talked earlier, which needed a custom setup. So basically, this is all the dependencies that we need, and this will be built in base image, and this is the commands that you would normally use. So basically, you do a build, and this is the name of the image, and the version is v1, and this is going to be the repository that we will push to, which is in Docker Hub in my account. So let's see that would work. Okay. Now, can't does that. What we see here, this is basically Docker file commands, copy run, and for each of this command, Docker will build a layer, just like it's very similar to what you would see in Git. So every commit is basically a layer. And on top of that, there's the new files and so on. So basically that's what Docker does. It builds layer one on top of the other for each command. And this is how basically things are reused. Okay. Is it not here? Okay. Okay, this is currently another bug, not gonna look at it, fix it afterward. This is already built and pushed, so we're not gonna waste time on this. Let's look at the other ones. Those should be working. So basically what we would see on the particular component Docker file is that you will be using the base image, and you will just add the code. And this is the command that runs at the end when the container starts. And basically, the container is an environment that runs a command, which is this one, and the life cycle of the container is basically wrapped around this command. So if this crashes, the container dies. So this is basically the, let's see how successful this looks like. This should be also pushed in the Docker.
When's a good time to ask questions?
Shoot. You can ask questions.
Sorry, I think there's a bit of lag from my side. How did you pick the base? Is there a way to think about it?
Pick what?
The base image, the base Docker
image
file image.
Yeah, that's a good question. So the ones, this is what I use. When you want to go to production, it's really important how you pick the base because there's a lot of concerns like security. So like any other library that you use from official sources, trusted ones. This is the official source of Python. And on Docker Hub, you can also see those official ones as marked. If you use a different one, you need to make sure there's nothing, insecure installed there, and there's like if somebody else, added on them, you can find bugs like you just saw here. At my setup, I forgot some things, and it could add instability to your code, to your platform. So always try to start from official sources.
Okay, that makes sense. Thank you.
Okay, this is basically how a successful build looks like. So you could see here that every command is a step, and it's built in a different layer that has a hash. Okay. Now, then you can also push it. We also have the commands here. So basically, this is how you would push to the repository, to my Docker cont. So it pushes each layer. It recognizes that some layer already exists. And sometimes you see also here that it reused layers from different images because it recognized from the hash that that layer already exists. Okay. Now also prepared here, basically the run commands for our components, and how this will work is basically you would see the same things that we just saw here, but instead of running them from the IDE, we're gonna use the these commands. So also the run commands have a few parameters that I set up, which are these that our code uses, and repdemq host, user, password, the name of the exchanges in the queues. And we also be using, this is how we use synchronize files. So this will synchronize the location of our models folder which is this, where the model was built. You can also delete it and we see it being recreated to this location inside our container. And the same we see here. Now, if we're gonna run this on our host, we will see this. Let's see here. This should be okay. Our API is running, and now our workers. Now the host. This is how you connect to your host. So basically, to my host machine from inside the container. So because our RabbitMQ is a daemon that is exposed inside the host and not the container. Okay, how I make that disappear? Okay. So basically, this also has the port 14 of port 80 so that we can test it now. And basically, we'll do again on localhost and train, and this should trigger the train. Okay, seems like it started. And we can see here in the API, we call train. This message was sent to the queue. If you look to the worker did a training. It saved the model. It notified the API, which got the message and wrote the cache. And now if we look here, yeah, see, the model appeared in the synchronized folder on our host. So, okay, now let's see, we can also test our predict, which is, we should get, no, sorry, yeah, test it on a different. So yeah, we got the class tool, which is hard-coded. So, and we tested on the 5 PNG that we also tested before, but there's a bug there, so I have to fix that after. So yeah, this is basically what you have to do to containerize those two services, the worker and the API. And basically now it's ready to move forward and try to deploy it to the cloud. Okay, let's stop these processes. Okay, now let's move on here. Now, what we're going to use to deploy the cloud is Kubernetes. Kubernetes is basically a container orchestrator. So this will basically spin up containers and orchestrate infrastructure around it. So load balancers, network communication between the containers, and file volumes, because here we mounted our models folder in both containers, but when you go and scale, this is not that easy because you will have more host machines or virtual machines where all your containers lie, and you cannot have you cannot have a shared folder on one of those machines. So you need to have a different storage location, like an NFS server or Samba server or things like that, that basically offers a shared folder to other containers, to have this synchronized. So this is a very important aspect of scaling. The part of your application that is stateless and the persistence. So in our case, we only need to persist the models. So these folders need to be accessible by all the containers. Even if we have 1 or 2 containers or 100, they all need to use the same shared folder. Okay. So Kubernetes is gonna help us do that. So we're gonna look now at building the resources for Kubernetes. Let's see how a Kubernetes cluster looks like. Basically, there's a master, which a few components that I'm not going to go into, and it will have agents, so or nodes. Each node is basically a virtual machine, and you can scale this depending on your needs. So we'll start with 1 node, and then we'll scale to more nodes. Also, our application will start as two pods containing the same API, and 3 pods containing the same worker code, the same API code. And basically, we're going to see how all this works tied together. Okay. Let's see. Now, basically, this is just a basic. So Kubernetes is basically you describe configuration files for each resource, and then you just tell it to deploy that resource. On top of that, when you try to, I don't know, deploy more components, package more components in your deployment, and things get complicated, you need eventually to think of a solution of how we're gonna package all those files. So our application have basically 5 resources, and I also used a package manager for Kubernetes, which is called Helm. And I created a Helm package where I defined our resources, and it also has templating. So basically, you could add templating and variables inside your resource to better management and configuration files. Okay, so this is what a default package would look like. Okay, and after that, I created a new commit where we adapted that to our needs. So, okay. No, not here. Okay. So let's close some of the things. Okay. Now, this is how a configuration file looks like. Here we have a lot of variables that we input. and it's a little bit, I don't know, harder to understand at first glance. I also exported the final uh, versions of this, which would be this. This is how final version would look like. So basically we defined the image that we're going to use, some port configurations, the environment variables that we're going to supply from our configuration file, which is values.yaml, the volume mount, which is very important. So basically we're going to mount at this location the volume that is described here. So we're going to create, it's called the persistent volume claim. This will create in our Kubernetes folder persistent location that is managed by
Another question.
And this location will be mounted basically on all our pods. So a pod is basically the Kubernetes resource that is wrapped around the container, and it makes sure that the container stays up, is connected to the network in the cluster. If the container dies, the pod will restart the container. So basically that service will be restarted if you have a crash, maybe, I don't know, memory leak or something like that, or a network issue that creates a timeout and your code crashes. The pod will make sure that the service will be restarted, and if you handle your code correctly, basically will restart and consume the same message in the queue. So this will allow you to have a more stable and robust deployment. Okay, so
sorry, can I ask another question, please?
Yeah.
Is there any production environment where you were able to use GPUs?
GPUs?
Like, were you able to use GPUs on a production environment, or is it mostly CPU that the framework is using for the predictions?
Yeah, I haven't used GPUs yet. Docker has support for CUDA. I'm not sure if Kubernetes has that support. Probably it does. I haven't tested to that. I'm not sure. I probably will do a continuation to this if somebody is still interested. It's like a lot of complexity here. I just wanted to, I don't know, show people how much work it involves in taking something to production. But yeah, if people are interested in seeing this, use also GPU, I'll probably try to do a follow-up presentation on that.
All right, thanks a lot. Yeah, we were talking on the chat whether normally you would use CPU or GPU for predictions. I mean, currently this API has a train method on it, which is synthetic, right? I mean, you would normally just put the prediction possibility on an API, and you'd already have a pre-trained model, or I'm not sure. Maybe there's a scenario where you would actually let inside the API to train the data.
Well, this
what do you think?
This trains the data. So basically, the model was trained. It's just that it trains so fast because it trained on a set of images of 8 by 8 pixels. So it's like really fast.
Yeah, tiny images.
Yeah.
So are there situations where you would provide this sort of API where you train on a certain data set, or do you usually just provide trained models on which you just do predictions?
Well, depending on your use case. So like I said, you can have a really big model and let that model be used by everyone you, I don't know, sell your service to. But there's a lot of cases when people have their own data sets. So if you're going to do I don't know, try to detect someone's particular writing. Okay, so then you would have maybe a model for each company, because you don't want to, you cannot mix in, I don't know, in production scenarios, you can put all your data together. You have like 5 clients that you give your application to, and they each have their data set, and they don't want to share it because GDPR, because I don't know, competition and so on. So you need, in that case, to build models separately.
Yeah, that makes sense.
And do predictions based on each person's model. So basically, this is the scenario that I'm showing how you would handle this and how you would scale, because if you're gonna have like 100 customers doing 100 models in parallel, and at request, like you have here, you have an API and you trigger the training whenever you want, and you want to use your train model as soon as it finishes. That's what people usually want in production. So yeah, basically this aspect I'm trying to show.
Okay, so just a follow-up question, because this is something that Valentin K asked
Okay.
higher on the chat. So TensorFlow tends to occupy the whole GPU memory. In example, second training may easily fail because the GPU memory would already be taken. I guess this is the situation where we would consider the same Docker container to be used for the training, but I guess a separate one would be made in this case with a separate GPU allocation, a separate GPU memory allocation.
So basically, Kubernetes gives you a lot of power of where you put things and how they run. And one of that would be, so we're talking here about RAM, not GPU RAM. So, yeah, so basically you can define resources for a particular pod, which manages the container. And you say requests and limits. Request is the amount which that the container uses at idle. So basically, it starts with 100 mega of CPU and 128 mega memory, and you can put a limit on how much it uses. So basically, you can put a limit on the CPU, let's say 1000, right? And you can put here like 256. And this is how much one container will be using. If it tries to use more than the memory limit, the container would be killed, and it will be restarted. So this is how you handle resource management in Kubernetes. There is also, depending on which nodes you have, like you can have a lot of powerful nodes. You can don't put limits on that and have containers, pods running on a single node. So you can use node selectors, affinity, like which type of nodes to put them on. Can put labels on nodes and tell pods you can be scheduled only to particular nodes and so on. So basically you can use that to isolate a container working on a very powerful node that has a lot of GPU, RAM. So this will make sure that if you put one worker on one GPU node, basically you would not have this issue of two nodes trying to clog up the same GPU memory.
So I guess these are different parameters. There's a limit on the RAM, and there should be like a different parameter for.
Yeah, so this is CPU and RAM. I'm not sure if you can do this also for GPU. I'm not sure if they have support for that, but you can surely use this. So you can isolate one worker per one virtual machine or one node, and in that way you cannot have two workers at the same time trying to get the same resources from a node, from a GPU, and die.
I think I understand. So it's something that needs to be determined. Thanks very much for your time. I feel like I'm taking up a bit too much time. Thanks a lot.
Okay, so basically, yeah, let's see.
Grazie Claudio.
Welcome. Yeah, so let's see the time, okay. I won't be going then too much into this. So basically we have a resource for the API, which will have two replicas. This is the precedent value claim that will generate a shared folder for all of our components. This is the worker, the same parameters, different image, and the same volume. There's also a service that exposes the API using in the cluster using the HTTP 80 port. And there's also the ingress, which is basically the load balancer in front of the cluster that funnels all the requests. And
Sta arrivando Raresh a mangiare con noi un pezzettino di carne.
And
Sta arrivando.
And we basically funnel all the requests to our API. Okay, so let's see this working inside the cluster. I have installed Minikube. Minikube is basically a one node cluster that you can install on your machine and test it. So let's see. It's already installed, and I installed the package with the RabbitMQ, which basically we used earlier to do the tests. So this is already installed, and I will just install where is it? I did that. Ingress. This is K9S. It's a tool that you can easily connect to the cluster and better see the pods. So basically we install ingress. The first two are the ingress that are starting up, and these 5 are the 2 APIs, and these 3 are the 3 workers. Now we're gonna start to, in just a second, it's gonna be up. And let's see. Let me just configure the host file. So we can test. And if we do the train, okay, let's see that they're up. Just a download images takes a while. Just anything here. There. What's the setup for Azure? It's my internet slow. Why is it taking so much? Let me see if the cluster Azure is also up. I can then show you how you can scale even more. Yeah, this is also up.
Thanks a bunch for your efforts. Are we going to get a recording of this webinar lately, like on our emails?
Yes, we are recording. Maybe I'll put it on a drive and share the link on the meetups page.
Yeah, it's a lot of information, so yeah.
Okay, thank you.
Pleasure.
Okay, so all our components are running. Let's see the logs on them. So you can see the same logs at the top of the API and also the worker. Now, let's see what will happen. Let's look a little bit of how the queues are working. So this is basically the worker queue. So an API component will put a message in a fan out. Yeah, it's shouldn't say fan out there. Okay, it should be a direct exchange. And the message will end up in the queue. So basically, if we do quick trains, you should go 1, 1, 1, 1, 1, and then again. And we have 3 workers. Let's see what happens when we do our first train. Okay, our first train started. Let's look at the workers. Should see it in one of our workers. Third one, yeah. So we saw our third worker pick it up. It would be the training and also put the message in the cache queue, the API queue. So now if we look at the API pods, this one only reloaded a cache. So this is not the one that got the message in the API. This one should be, yeah. So this one got the message, send the train message to the queue and receive the reload. So basically only one API triggered the training and both APIs reloaded the cache when the training was done. Now, if you're gonna do a bunch of triggers, we should see them land on different API containers. So basically we have 3 triggers here on this one and the other one. We have another 2. And total cache loads 5 here, and should be also 5 here. Yeah, so 5 here. So basically, now you can start to add how many API pods you need in order to handle the load for your web app, and you can also scale how many workers you need to handle your training load. Yeah, so if we do we have 1 train here, 2 here, and another 2 here. So we have all 5 trainings handled by our workers. And if we do the predict, we should see this also in, yeah, we have, sorry, predict here, and another predict here. It's big.
Claudiu?
Yeah.
Sorry. Do you think you can resume like in 10 minutes to let some time for questions for the people that maybe didn't put that during the presentation?
Yeah. Well, basically, the presentation is over. I could also show in Asia, where you can scale to more nodes and more pods in it. So, but basically, this is it. This is how you would scale application. And here we can now add as much worker nodes as you want. We can also, let's see. We can now scale to 5 workers. Now told Kubernetes to add 2 more workers, and then you can see them spinning up. Yeah, and they're already running. If we do a bunch of trains, we would see. Yeah, now you can see the new ones also picked up. Yeah, we just added 2 more workers to the queue, to the worker pool, and they started doing trains. Okay, any more questions?
So can you add workers in real time or something similar to this? So like if you want to do a change, like can you do it in real time?
What do you mean by real time?
So you want to add more workers. So you
I just added 2 more. So why is not working? So we currently have 5 workers. 1, 2, 3, 4, 5. Yeah. I just ran the command that scaled to 5 workers. I can go now, scale down to 2. Yeah. And you can see 3 of them terminating, and they'll shortly disappear.
And the assumption is that they do not, that none get interrupted when more added.
Yeah, so the ones that are running are running without problem because we're using the queue. This is why we wanted to use the queue, because this queue handles the processing of the jobs. So basically, you subscribe to start consuming a queue, and a message comes in. Okay, you say, okay, the worker says, okay, I'm gonna process that one. It locks the message, it starts processing, and if it finishes correctly, it will acknowledge the message. And the acknowledgement of the message will delete the message from the queue. If the message is not deleted, then the message remains the queue. So if your code breaks, or I don't know, you scale down and the pod disappears, that worker disappears without finishing the task, then basically the message still remains the queue. So when the connection to the RabbitMQ queue of that worker dies, then it knows that that message is no more linked to any worker. So it's again waiting for a worker to process it. So when a new worker is free, it picks up the same message, starts again the job. If it finishes, it acknowledges the message, and you have the triggering of the reload of the cache happening, or whatever you want to do at the end. Basically, this is how you're sure that everything happens, and your code that breaks doesn't, I don't know, use the flow of your app or something like that.
Got it. Thanks.
Yeah, you can scale now. I'm not sure how many resources you have, but I can basically scale, let's say, 50 nodes. So yeah. When you get to this stage, it's really fun how easily you can scale things, but until you get to this phase, like there's a lot of boring code you have to go through that I've shown you. So yeah, but a good, I don't know, architecture of your code and your components can help you do a lot of things in the end. Okay. So, it's like it froze. I think too many parts broke it. No.
If there are other questions, don't hesitate.
Yeah. So the API server broke. Probably, yeah. Let's scale down too much.
If there are no other questions, I guess I'd like to ask another one. Have you ever had a model that's too big for the cache? Is the cache also something that you specify in the configuration files, or is there a hard limit to it?
Cache is a limit to how many RAM you have. So basically, if you can put this in the cloud, you can get virtual machines nodes with a lot of RAM of 128 gigs of RAM. So
that should be sufficient.
yeah, so that's RAM is not the problem. The problem is processing power. So you have a limit on the CPUs. But depending on the code, you can, I don't know, parallelize in multiple cores. And again, GPU, I'm not sure what's the limit on that. So, yeah.
All right.
Yeah, so I broke the server. Oops. Okay, I started. So yeah, I started too many pods, then it had if I started with more 4 megabytes of RAM and 4 CPUs, maybe that can work. Any other questions? Did you manage to understand anything that I explained? There's a lot of it. That's why I try to do it in commits. So later on, when we look at it, if you're gonna look at it, you can try to see how much more work it is to build it in microservices, and so we can later scale it.
Yeah, definitely. That was a very good idea to put the code in commits. Right now, we don't really have the problem of having to do this from top to bottom, but when we do, it's going to be gold.
Yeah, daily production is.
Do you think this could be replicated with our own model? Let's say we change what you use, and will it be available, and we plug and play or something that we can change?
So can you repeat? You want to replicate this with your model?
Yeah.
Yes, so I try to put as much information there to help you do that. Basically, setting up the environment is what we need to do. This is the dependencies. If your Windows is going to be a little bit trickier, sorry. On Linux should be pretty the same as Mac. You can basically use this with your model. This is why I layered the application just need to basically handle this, the predict and train in the ML module. You put your train code here, yeah, and basically
just predict. I mean,
your predict code here, and you
enough,
need to
yeah.
build the images. You need to build the images with your code, push them. Hope not my entire OS crash. Okay, so this is, let me scale again down. If we can scale again now. Yeah, no, I just stopped it. It's wrong, like system too much. Okay, should find out. So yeah, so basically you need to build these images. You have the run commands here. and basically you push to your Docker account in Docker Hub, and you will have to come here. Basically, the
set up a
repositories.
small to put it on our GitHub, and maybe to read me at least with the steps in order. What we have to do is like
the steps are here.
Okay. Yes.
Basically, you try to replicate this.
Yeah.
And yeah, you can contact me if you need help and so on. Because I don't know, if more people want to replicate it, maybe we can schedule like a day of workshop or whatever. Jump on all on a call and we try to figure things out and have it run on your system also. Should be basically simple. But this is just get all the dependency working. That's the usual tricky part. After you have a working cluster, Minikube or whatever, you can basically do it faster.
Are there any more questions? If not, maybe we can stop here and we'll see. You can always ask questions directly to Claudiu. I added his LinkedIn profile on meetup description, or write on the meetup, and we will forward to him if you have any questions. So we will put the video, what we registered on the GitHub, and if you have some code, the code, if it's open to be shared, we'll add it on the GitHub.
Yeah, it's also on my GitHub account. I'll post a link after it, and just need to fix the 2 bugs, and I'll push it and I'll post it on the event, GitHub event.
Okay, well, thank you, Claudiu. Thank you very much for the presentation. It was, there are many concepts at least for me. So I'll have to do it by myself, maybe just replicate the same code with the same support vector machine model, and then try to plug another model to see if it works.
Yeah.
And then I'll see. Thank you very much for this presentation. And see you at the next meetup.
Okay.
Hello, everyone. Bye. I will stop now the recording.
Thanks. Bye.
Bye.
Thanks very much.